spatial mapping experiments. Heather Fong, University of British Columbia.
Hi. So this summer I did an summer internship at Chalk River, Ontario. And one of the great things about working in Chalk River was I got this fabulous outfit decked out from head to toe. Okay. Right, so the topics I'll be talking about include a little bit about the Canadian Neutron Beam Center, CNBC, and I'll be talking a bit about the experimental technique called neutron scattering, as well as the project that I was involved with, and future projects that spawn from that, and finally I'll end with some special thanks. So here's a map of part of Ontario, and right here is Toronto, and up here is Ontario, and 2.5 hours drive is Chalk River, where I did my internship. And so a close-up view is Chalk River Labs, where I did my internship, and along here is the Ottawa River, and over here is Ontario, and the other side is Quebec. So the Canadian Neutron Beam Center is a part of National Research Council, NRC. And it's located in Chalk River Laboratories, and it's operated by the Crown Corporation of Atomic Energy of Canada Limited, ACL. And this is an image that I took of ACL from the Ottawa River. So neutron scattering is an experimental technique to study materials. And where we conduct these experiments is at the National Research Universal, NRU, and it supplies Canada's only major source of neutrons, and they supply all the neutrons for our CNBC experiments. And it also produces medical isotopes, test fields, and other in-core materials for the nuclear industry. And it's been in operation since 1957, and it produces up to 60% of the world's medical isotopes. So neutron scattering, how it works, if you have your research reactor where your source of neutrons come in, so NRU, and these fast-moving neutrons are then slowed down using heavy water, so when they hit the neutron beam, it'll hit a monochromated crystal that'll separate it into a specific wavelength and energy that you want. And then these neutrons will then hit the sample that you set up, and then the diffraction pattern from these neutrons will let you know what properties that your sample has. And so an application of neutron scattering is for spatial mapping. And what you do in spatial mapping is you measure some intrinsic properties such as residual stress, strain, texture, and imaging. And some samples that you might use include pipes, train rails, and turbine discs. And you can evaluate the manufacturing properties, manufacturing processes such as heat treatment, surface modification, and stuff like welding. And what is good is that it's non-destructive, so it doesn't harm the sample. And what makes it different from using X-rays is that the neutrons penetrate the entire volume of the sample, whereas the X-ray only examines the surface. So where I did most of my work was at the L3 neutron diffractometer, and here's a photo of L3, and here's its corresponding CAD diagram. And this is the neutron wall, where the neutrons come from, and right here. And then this is where the drum, where the monochromatic crystal is located, and here it's right here. So on the L3 diffractometer is a sample table. It can translate and rotate onto itself, and over here is where it is on the actual diffractometer. And so what I worked on was the alignment procedure that we use, where we set up the sample table before every experiment that we conduct. And what we do is we align the sample's point of interest with the neutron beam. And how we use that is with a wire, with the center being the sample's point of interest. And then we use telescope to check the alignment, similar to what a surveyor does. But the problem with this current procedure is very labor-intensive, it's time-consuming, and it's all manual. So what we want to do for our new procedure is we want to make it more automated, whereas we define a virtual coordinate system with the origin of the sample table's center of rotation. And then we want to track the wire's position relative to the new coordinates. is its ability to scan in 3D. And how we do that is we use something called a Metroscan 3D laser scanner. And it uses the C-track and the reflectors to produce a 3D model of the sample. So you can see that there are some reflectors all along the Metroscan so that the C-track can pick it up. And so what things that we scan include samples such as this beam port, and this is its corresponding 3D model. And another thing that we scan are pipes, which is what we usually do in our neutron scattering experiments. And this is its 3D model. And just for fun, we decided to scan someone's head. So this is Drew. He was a good sport and he let me scan his head. And this was his 3D model, which is pretty good. It looks kind of like him. And another thing, what we use the 3D samples for is we use them to run simulations. So we have a program called Scan, which is developed by the Open University, and it's able to read the model, and then it can virtually position your model on the diffractometer, and then, so you can see here that here are some different diffractometers, and then the sample sits right on the sample table. And what it does is it can run a simulation of the experiment, and so then that it generates these commands, so when we run the actual experiment, we know what controls to use. And so for testing, before we could commission this project, we had to test how accurately the C-track measures. And so C-track has an uncertainty of about 35 microns, while the control system has 5 microns. And we wanted to track the reflector's movements on the sample table. And so we measured its coordinates, and we compared the C-track and the control system's coordinates. And we measured things such as the position, the orthogonality between X and Y, and the sample table rotations. And so here's a graph of some of the tests. So this axis corresponds to the control system, and this corresponds to C-track. And a slope of approximately 1 means that there's a good correlation between the two measurements. And so this is for the x-axis, and this is for the y-axis. And then we also took this one where you notice that the C-track's uncertainty range doesn't quite fall within the shaded region, which is the control system's uncertainty. So in conclusion, we know that the C-track can track a point's position so that it gives a similar coordinate to what the control system detects. However, it does occasionally fall outside the range of uncertainty, so in order to maximize the accuracy, we need to calibrate the C-track regularly. And so for alignment using the VX elements, we use dynamic tracking, and we define the sample table's reference system, and we create a tracking model